Europe is experiencing its greatest mega-projects boom in history. Tunnels are being bored through the bottom of the ocean, railways are stitching together countries, and a global scientific revolution is taking shape. From a revamped rail through the Baltics countering Russian influence to a $34 billion push for clean energy, these are the biggest megaprojects under construction in every European country, starting with the deepest underwater tunnel taking shape in Norway. Every day, thousands of commuters along Norway's western coast face the same frustrating reality. Their drive to work includes sitting on a ferry for 45 minutes, watching the clock tick, while the boat crosses the Bokna Fjord at a leisurely pace. When the weather turns bad, which happens often in the North Atlantic, the ferries just stop running. Travelers get stranded on either side, sometimes for days. A route between two cities 200 kilometers apart becomes an all-day ordeal. This isn't some remote wilderness crossing. The route connects Stavanger, Norway's fourth largest city and the heart of the country's oil industry, with Bergen, the second largest city. These are major economic centers that desperately need reliable connections. But the deep fjords carving through the coastline make road travel nearly impossible. The current journey requires multiple ferry crossings, each one a potential delay. Trucks carrying freight between the cities lose hours waiting at terminals. Business travelers build entire extra days into schedules just to account for weather cancellations. Norway looked at this problem and decided the solution was to drill a tunnel 390 meters beneath the seafloor, deeper than any other underwater road tunnel ever built. The decision came after decades of systematically eliminating ferry crossings on the coastal highway network. Norway has oil wealth and takes a century-long view of infrastructure. Ferry services cost millions annually to operate, need constant government subsidies, and fundamentally can't provide the reliability a modern economy requires. A tunnel costs billions up front, but it works for generations with minimal maintenance and operates regardless of what the North Atlantic throws at it. The Rogfast tunnel will run 27 kilometers under the Bokna Fjord. At the deepest point, drivers will be 390 meters below sea level. If you stood there and looked straight up, there would be the equivalent of a 130-story building worth of water and rock above your head. The tunnel will have 2 lanes in each direction and will cut nearly an hour off the drive time between Stavanger and Bergen, while eliminating every bit of uncertainty that comes with, depending on ferries. Construction started in 2020 using tunnel boring machines specifically designed for extreme depths. The machines drill through solid granite, carving out space wide enough for 4 lanes plus shoulders and emergency areas. Behind each boring machine, crews install reinforcement to prevent collapse. Steel mesh, rock bolts driven deep into the walls, and layers of sprayed concrete to contain the immense pressure from the rock. That pressure is the real engineering challenge. Rock 390 meters underground doesn't just sit there peacefully. It's under enormous stress and wants to expand into any open space created by drilling. Without proper reinforcement, tunnel sections would collapse as the rock shifts and deforms. Every meter of tunnel requires careful analysis of the rock conditions and custom reinforcement designed for that specific section. Construction has not always gone according to plan. The boring machines keep hitting underground fractures and aquifers, flooding work areas with water under tremendous pressure. Industrial pumps run around the clock, removing thousands of liters per minute just to keep the construction areas dry enough to work in. Once the tunnel opens, those pumps will keep running indefinitely. Stopping them would mean flooding. The gradient presents another challenge. You can't just plunge straight down 390 meters and climb back up. Trucks couldn't handle slopes that steep. The tunnel descends gradually at about 3 to 4%, which means it needs to be much longer than the straight line distance between endpoints. Drivers will spend roughly 35 minutes making the crossing, much of it either descending into the depths or climbing back toward daylight. Emergency systems have to work at depths no other road tunnel has faced. If something goes wrong at the lowest point, emergency services are 390 meters of vertical distance away, plus kilometers of horizontal tunnel. The design includes emergency shelters every 250 meters where people can wait for rescue, along with fire suppression systems and ventilation powerful enough to reverse airflow and push smoke away from evacuation routes. Norway has extensive experience with tunnel safety. The country has hundreds of tunnels through mountains and under fjords. The ventilation alone requires massive fans and sophisticated controls to manage air quality and temperature in what's essentially a nearly 400-meter deep cave filled with vehicle exhaust. The $1.9 billion cost reflects these complications. Drilling at extreme depth requires specialized equipment, highly trained workers, and constant monitoring. Every meter costs significantly more than tunnel construction near the surface. Norway can afford this because of oil revenues. But even for Norway, spending nearly $2 billion to eliminate a ferry crossing raises questions. However, the economics work if you calculate long-term. The ferry operating this route now loses money every year and needs government subsidies. Operating costs include fuel, crew wages, maintenance, and the fact that ferries don't run 24/7 or during storms. The tunnel will operate continuously with minimal staffing, no fuel costs, and maintenance intervals measured in decades. Over 50 years, the tunnel probably costs less than continuing ferry service. There's also the economic value of reliability. Businesses along Norway's western coast currently factor ferry schedules and weather delays into every decision. Tourists avoid the region in winter when transportation becomes too unpredictable. A tunnel that works regardless of weather could transform the regional economy by making the coast genuinely accessible year-round. Norway is speeding ahead with the project. The boring machines have successfully drilled through the deepest sections, the parts with the worst rock conditions and highest risk. With construction on pace, the project is scheduled for completion around 2027. With the Rogfast tunnel, Norway will have pushed underwater tunnel construction to new depths. If Norway can drill nearly 400 meters underwater and operate safely, it proves that undersea crossings previously considered impossible or too expensive are actually feasible. While Norway drills beneath its fjords, 3 Baltic countries are trying to reconnect themselves to Europe with a railway that's been stuck in planning for 30 years. Estonia, Latvia, and Lithuania inherited their railway systems from the Soviet Union, and those systems were built to Soviet specifications. Not only are these tracks slow, it involves transferring all cargo between different train cars because the tracks don't match. The delays cost money, the transfers damage goods, and the whole process makes Baltic businesses less competitive than their European counterparts. This wasn't an accident. The Soviet Union deliberately used different track spacing partly for military reasons. Invading armies from the West would find their rail equipment useless on Soviet territory, and partly to tie the Baltic states economically to Moscow. After independence in the 1990s, all 3 countries wanted better connections to Europe, but changing their entire existing rail network to European gauge would cost tens of billions and take decades. The old Soviet tracks stayed in place because there was no alternative. Rail Baltica solves this by building a completely new railway on European standard gauge, running 870 kilometers from Tallinn through Riga to the Lithuanian-Polish border. Trains will travel at speeds up to 249 kilometers per hour, cutting the Tallinn-Warsaw journey from over 13 hours to about 5. The line will connect the 3 Baltic capitals while serving regional cities and linking to major ports and airports. The idea first appeared in the 1990s, then spent 2 decades stuck in planning while the 3 countries argued about routes. Every town wanted the railway to pass through their territory. Every country wanted control over major stations and connections. Estonia, Latvia, and Lithuania share a Soviet past and current EU membership, but they're still 3 separate countries with different priorities and competing interests. Reaching agreement on where the tracks would actually go took nearly 20 years. The European Union finally broke the deadlock in 2017 by offering to cover 85% of construction costs if the Baltic states could present a unified plan. That financial incentive forced compromise. The agreed route runs roughly along the Baltic coast, connecting Tallinn, Riga, and Vilnius, while branching to Kaunas and linking to regional airports. Construction began in 2019, with all three countries working simultaneously on their sections. Building a high-speed railway through the Baltics involves terrain that Western European rail planners rarely encounter. Long stretches pass through sparsely populated areas where there are barely any towns to serve. The route crosses extensive wetlands and peat bogs that can't support heavy structures without special foundations. Winter temperatures regularly hit -20 degrees Celsius, requiring track systems designed to handle extreme cold without cracking. The real complexity comes from coordination. Rail Baltica isn't one project. It's three separate national projects that need to connect seamlessly at borders. Estonia handles construction on Estonian territory, Latvia on Latvian territory, Lithuania on Lithuanian territory. Each country uses its own contractors, manages its own budget, and follows its own procurement processes. Getting all three to build to identical specifications, meet at borders on schedule, and create unified ticketing and operations systems requires constant coordination meetings and endless bureaucratic negotiations. Estonia has moved fastest. Significant sections of track are already laid, and the Tallinn-Pärnu section is approaching completion. Latvia's construction has progressed more slowly, partly because the route passes through Riga and requires building a new central station in the middle of the capital city. Lithuania is dealing with the Kaunas connection and challenging wetlands in the southern sections that keep requiring more extensive foundation work than initial surveys predicted. The budget started at $5.8 billion but keeps climbing. Peat bogs turn out deeper than expected, requiring more foundation work. Archaeological discoveries pause construction while teams excavate and document sites. Environmental reviews force design changes to protect habitats. Every delay in one country affects the other two, creating cascading schedule problems. For passengers, the railway should boost business travel and tourism. Right now, traveling between Baltic capitals is inconvenient enough that most people fly to one city and never visit the other two. Fast rail connections would make visiting all three capitals in a single trip practical. Business travelers could attend meetings in different cities on the same day instead of planning separate trips. Rail Baltica reduces Baltic dependence on Russian infrastructure. The old Soviet gauge tracks connect easily to Russia but poorly to Europe. Rail Baltica reverses that. European connections become easy, while Russian connections remain complicated. Russian officials have made vague statements about the project being provocative, which the Baltic states consider confirmation that they need alternatives to Russian-controlled infrastructure. Current schedules show the first sections entering service around 2026, with the full line operational by 2030. Those dates have already slipped multiple times and will probably slip again. Estonia's sections might open first, while Lithuania's portions could take longer. The three countries are trying to coordinate so that at least some cross-border service can begin as soon as any continuous section is complete, rather than waiting for the entire 870 kilometers to finish. The first new international railway built in Europe in decades is taking shape across three small countries that spent half a century under Soviet control. Whether it succeeds depends partly on construction quality and partly on whether enough freight and passengers actually use it to justify the investment. From the Baltics building a railway to reconnect with Europe, we head south to a railway trying to reconnect two countries with a complicated shared history. The train from Budapest to Belgrade takes 8 hours to cover 350 kilometers. That works out to about 45 kilometers per hour, barely faster than a bicycle. The railway uses track from the 19th century that winds through every small town along the route, with rails so worn that trains can't safely exceed 50 kilometers per hour in most sections. Nearly everyone drives or takes a bus because the train is too slow to be useful. During the Austro-Hungarian Empire, this corridor was an important rail link connecting Central Europe to the Balkans. After World War I, the route remained significant for freight and passengers moving between Yugoslavia and the rest of Europe. But decades of underinvestment left the infrastructure crumbling, and by the time Yugoslavia collapsed in the 1990s, the railway barely functioned. Neither Hungary nor Serbia could afford to fix it. Both countries had more urgent infrastructure needs and limited budgets. Cross-border traffic between the two wasn't heavy enough to justify spending billions on railway upgrades. the line continued deteriorating, with sections occasionally closed entirely when track conditions became dangerous. China offered a solution in 2013. As part of the Belt and Road Initiative, Chinese companies would modernize the entire Budapest-Belgrade railway, with financing through loans from Chinese state banks. Hungary and Serbia would get modern infrastructure without paying up front, and China would gain another piece of its planned freight corridor from Greek ports through the Balkans to Central Europe. The deal signed in 2015 called for upgrading the entire route to allow passenger trains at 200 kilometers per hour and freight trains at 120 kilometers per hour. Travel time between Budapest and Belgrade would drop from 8 hours to under 3. Chinese companies would handle most construction work using Chinese equipment and Chinese financing. Construction started in Serbia in 2017. Chinese contractors tore up old track and built new foundations, working at a pace that seemed remarkably fast by European standards. Chinese construction crews operate longer hours and face fewer regulatory obstacles than European contractors typically encounter. Entire sections of track were replaced in months. Hungary's portion immediately hit problems. The European Union raised concerns about procurement processes, arguing that Hungary hadn't followed EU rules requiring competitive bidding for infrastructure projects. Brussels suspected the Chinese deal was negotiated without proper transparency, potentially violating regulations that Hungary, as an EU member state, was supposed to follow. The dispute lasted years. Hungary eventually restructured the deal to satisfy EU requirements, but this delayed construction by nearly 4 years. By the time Hungarian work finally started in 2021, Serbia's section was already substantially complete. The modernization involves replacing most of the old track entirely, rather than trying to renovate it. Curves get straightened where possible to allow higher speeds. Stations are being rebuilt. New signaling systems are being installed. The line is being fully electrified to replace the diesel locomotives currently used. Some sections require extensive earthworks to create flatter gradients that high-speed trains can handle. Serbia's section should be fully operational by 2025. Hungary's portion might be complete around the same time if no more regulatory issues appear. Whether both sections finish simultaneously and actually work together as one continuous high-speed line remains to be seen. The two countries were supposed to be upgrading a railway together, but ended up on completely different timelines working with the same Chinese contractors. Chinese financing is building railways through European countries that need infrastructure but lack the resources to build it themselves. The arrangement benefits everyone in the short term. Serbia and Hungary get modern railways. China gains influence and potential freight routes. Whether it creates problems long-term depends on factors that won't be clear for years. From railways financed with Chinese loans, we head to Greece, where an old airport is being transformed into a massive coastal development. Athens hosted the 2004 Olympics and built a spectacular new airport to handle the influx of visitors. The old Athens International Airport at Ellinikon, which had served the city since 1938, closed down and sat abandoned. For nearly 2 decades, 620 hectares of prime coastal real estate just 7 kilometers from downtown Athens slowly deteriorated into crumbling terminals and overgrown runways. Greece's economic crisis made selling the property nearly impossible. The government desperately needed money but couldn't find buyers willing to pay during the depths of the recession. Environmental groups wanted the land turned into a park. Local residents had mixed feelings about any development. The site sat in limbo while successive Greek governments argued about what to do with an abandoned airport sitting on some of the most valuable coastal land in the Mediterranean. The breakthrough came in 2014 when a consortium led by Greek company Lambda Development purchased the site for €915 million, with plans to transform it into Southern Europe's largest coastal urban development. The vision included residential towers, hotels, a casino, shopping districts, offices, a marina, parks, and beaches, essentially building a new neighborhood from scratch on the abandoned airport grounds. Financial troubles delayed actual construction for years. The development plan required significant changes to satisfy environmental regulations. Greece's bureaucracy moved slowly on approvals. the consortium struggled to secure all the necessary financing. Ground was broken ceremonially multiple times before real construction finally began in 2021. The current design spreads €8 billion worth of development across the entire 620-hectare site. The old airport terminals will be demolished, runways torn up, and the whole area reshaped into a mix of high-rise and low-rise buildings surrounded by extensive green space. 200 hectares will become parks, one of the largest urban parks in Europe, along with 3.5 kilometers of beaches and a marina for luxury yachts. The residential component targets wealthy buyers, both Greeks and international investors, looking for Mediterranean property. Luxury apartments with sea views are being marketed heavily in the Middle East and Asia. The pricing is deliberately high-end. This isn't affordable housing. It's luxury development aimed at the top of the market. A massive casino resort is part of the plan, trying to attract gambling tourism currently going to Monaco and other Mediterranean destinations. Greece legalized casino gambling partly to make the Ellinikon project more financially viable. The casino will be integrated with hotels and entertainment venues, creating a destination meant to draw international visitors beyond just those interested in ancient Greek ruins. Environmental groups fought the project for years, arguing that such valuable coastal land should be public park space rather than privatized development. Protests delayed approvals, and the consortium eventually agreed to increase the park space from initial plans. The current design dedicates more land to parks and public access than to buildings, a compromise that satisfied some critics while still allowing substantial profitable development. Construction is happening in phases. The coastal park and beach areas are being developed first to show progress and build public support. Residential towers are rising in sections designated for high-density development. The casino resort is progressing slowly, with design changes and permitting delays pushing completion dates back repeatedly. Infrastructure, roads, utilities, drainage, requires massive investment before any buildings can be fully operational. Greece's construction industry has struggled to handle a project this size. Local contractors don't have experience with developments of this scale, so international firms are handling major components, while Greek companies work on smaller pieces. This created tension with unions and local politicians who wanted more Greek employment, but Greece's construction sector simply isn't equipped for an €8 billion megaproject. Financing has been complicated throughout. The initial consortium investment wasn't enough to cover full development, so additional investors were brought in from the Middle East and elsewhere. Every time new investors join, plans get revised to reflect their priorities and concerns. This constant revision has slowed progress, but also made the project more financially stable. The real estate market dynamics matter enormously. If Greece's economy remains weak and property values don't increase, the luxury apartments and villas won't sell at prices that justify the investment. The developers are betting that Athens will become an increasingly attractive destination for wealthy Europeans and internationals looking for Mediterranean lifestyle, combined with European Union residency options. Tourism is the other major factor. The hotels and casino resort need visitors to be profitable. Athens tourism has grown substantially over the past decade, but most visitors come for ancient sites and Greek islands, not luxury resorts in the city. The Ellinikon project is trying to create a new category of Athens tourism focused on beaches, gambling, and luxury amenities. Current timelines suggest the first phases, parks, beaches, some residential buildings, will open by 2025 or 2026. The casino resort might open around the same time if permitting proceeds smoothly. The full development won't be complete until the early 2000s at best, and that assumes no major economic disruptions or financial problems. The abandoned airport site will definitely be transformed into something, but whether that something becomes a thriving luxury district generating jobs and tourism revenue, or expensive infrastructure with unsold apartments and struggling hotels, won't be clear for another decade. Greece is betting €8 billion that wealthy people want to live and vacation in Athens badly enough to make this work. From Greece betting on luxury development, we head north to Finland, where engineers are building something designed to last longer than human civilization has existed. Finland operates 4 nuclear reactors that generate about a third of the country's electricity. These reactors produce highly radioactive spent fuel that remains dangerous for tens of thousands of years. Currently, the spent fuel sits in temporary storage pools at the reactor sites, waiting for a permanent solution that every nuclear country needs, but few have actually built. Onkalo is Finland's answer, a facility being carved 450 meters underground in solid bedrock on Olkiluoto Island, designed to permanently store nuclear waste for 100,000 years. Not 100 years, not even 1,000 years, 100,000 years. A time span so long that when it began, modern humans didn't exist yet. The concept started taking shape in the 1980s when Finland's nuclear industry realized temporary storage wasn't sustainable. Other countries were talking about reprocessing spent fuel or waiting for future technologies that might make the waste less dangerous. But Finland decided on a different approach. Find the most geologically stable rock on Earth and bury the waste so deep that it can't possibly affect anyone on the surface. Then seal it away, essentially forever. The site selection process took years. Finnish geologists surveyed bedrock across the country looking for rock that had remained stable for hundreds of millions of years and would continue to remain stable for hundreds of thousands more. The bedrock on Olkiluoto Island is 1.9 billion years old, some of the oldest rock on the planet. It hasn't moved significantly in geological timescales and sits in an area with minimal seismic activity. Construction began in 2004 with excavation of the access tunnel, a spiraling ramp that descends gradually into the bedrock. Workers have been removing about 60,000 cubic meters of rock per year, slowly carving out a network of tunnels 450 meters below the surface. The rock is hard granite, stable, and relatively easy to excavate compared to the fractured, water-saturated rock that plagues tunneling projects elsewhere. The actual storage system is elegantly simple in concept, mind-bendingly complex in execution. Spent fuel will be placed in copper canisters, each one weighing 25 tons and designed to remain intact for at least 100,000 years. The canisters go into vertical holes drilled into the bedrock, surrounded by bentonite clay that swells when it contacts water, creating an impermeable seal. Once a tunnel section fills up, it gets backfilled with more clay and sealed. Eventually, the entire facility will be closed and sealed permanently, leaving the waste to decay in isolation. Every aspect of the design accounts for scenarios most engineers never consider. Glaciers could return during the next ice age, burying the site under a kilometer of ice. The facility needs to withstand that pressure without the ice forcing its way into the repository. Sea levels might change dramatically over tens of thousands of years. The bedrock must stay stable even if the Baltic Sea floods the area or recedes completely. Earthquakes, though rare in Finland, could theoretically crack the rock and create pathways for water infiltration. The copper canisters are being manufactured to extraordinary tolerances. Each one is a single piece of copper 5 centimeters thick, surrounding a cast iron insert that holds the spent fuel. The copper won't corrode in the oxygen-free environment 450 meters underground, and the cast iron provides structural strength. Manufacturing flawless copper canisters this size took years of development. Any weakness could compromise the containment over geological timescales. Testing has been obsessive. Finland built a full-scale demonstration facility to prove the concept works. Researchers have studied how bentonite clay behaves over decades, how copper corrodes, or doesn't, in various conditions, and how rock stress might affect the storage holes over millennia. The whole system has been analyzed, tested, and reanalyzed to levels that seem almost paranoid until you remember they're trying to contain radioactive waste for 100,000 years. One problem has no good solution: warning future humans. How do you communicate danger across 10,000 years, let alone 100,000? Languages change completely over such timescales. Civilizations rise and fall. Written records deteriorate. Some proposals involve creating a nuclear priesthood, an organization that maintains knowledge of the repository across generations. Others suggest building massive monuments with symbols designed to inspire fear without language. There's no satisfactory answer. The facility is actually operating now, at least partially. In 2023, Onkolo received its first spent fuel for permanent storage, making it the world's first operational deep geological repository for high-level nuclear waste. More tunnels are still being excavated, more storage capacity is being added, but the fundamental concept has proven itself. Spent fuel can be permanently stored deep underground in a way that genuinely isolates it from the surface environment. The total cost is estimated around 3.5 billion euros, though that figure will climb as more storage capacity gets added over the coming decades. Finland's nuclear power plants will keep operating for decades more, continuing to produce spent fuel that needs permanent storage. Onkolo will keep expanding until Finland's nuclear program eventually ends, at which point the whole facility will be sealed shut. Other countries are watching closely. Sweden is building a similar facility. France, the United States, and other nuclear nations have struggled for decades to find politically acceptable solutions to nuclear waste storage. Finland actually built one, proving the concept works technically, even if the political and social challenges remain difficult elsewhere. Onkolo doesn't solve every problem with nuclear power, but it eliminates one of the biggest: what to do with the waste. Finland's approach is brutally straightforward. Dig deep enough that the waste can't possibly hurt anyone, seal it with multiple barriers, and let geological timescales handle the rest. In 100,000 years, whatever civilization exists then might dig up the canisters out of historical curiosity. Or the site might be completely forgotten, buried under ice or forests or cities that haven't been imagined yet. Either way, the spent fuel will be 450 meters underground in copper canisters surrounded by clay, encased in bedrock that was already ancient when humans first learned to make fire. From Finland's 100,000-year solution, we move to Spain, where Madrid is trying to solve a much more immediate problem with its most ambitious urban development in decades. Madrid has an age-old problem running through its heart, and most people who live there have stopped noticing it. Just north of the city center, stretching for nearly 4 kilometers, sits one of the largest abandoned railway yards in Europe. Dozens of rusting tracks, disused infrastructure, and vast stretches of dead land, all of it sitting idle in one of the most valuable and densely populated cities on the continent. For decades, this strip of land physically cut off entire working-class neighborhoods from the rest of the city. The story of how Madrid decided to fix that problem became one of the longest, most complicated, and most politically bruised urban development sagas in European history. And the project that finally emerged from it, Madrid Nuevo Norte, is not just a real estate development. It is a full reimagining of what the northern half of the city could become. To understand why this took so long, you have to go back to the 1980s. Madrid's Chamartín railway station, built in the 1970s as a modern replacement for an older terminus, was functional but disconnected. The tracks feeding into it from the north ran on the surface, carving through neighborhoods, creating noise, blocking streets, and leaving the land on either side stranded. The city had been debating what to do with this corridor since before some of its current residents were born. The first serious proposal came in 1993, a plan called La Operación Chamartín that would bury the tracks and develop the freed-up land above them. It sounded straightforward. It was not. Over the next 2.5 decades, the project changed hands between developers, got entangled in competing political interests between the Madrid city government and the national government, attracted accusations of corruption, was cancelled, relaunched, redesigned, and cancelled again. By the time a final agreement was actually signed in 2021, the project had been in planning for nearly 30 years. What finally got approved is staggering in its ambition. Madrid Nuevo Norte will transform 2.3 million square meters of land into a brand new urban district built on top of buried railway infrastructure. The centerpiece is a completely rebuilt and dramatically expanded Chamartín station, renamed Madrid Chamartín Clara Campoamor, which will become the largest railway station in Europe, handling up to 350 trains per day and connecting high-speed lines running north toward the Basque Country and eventually France. Around it, 4 distinct neighborhoods will rise from scratch, featuring over 10,000 new homes, office towers, parks, schools, and a business district anchored by a cluster of skyscrapers that will create a new skyline visible from across the city. The most striking of those towers is already under construction. The Kaleido Tower, a 180-meter glass structure sitting adjacent to the station, is already finished and operational, housing IE University's business school. It offers a preview of what the district is eventually meant to look like: modern, dense, walkable, and connected. But Kaleido is essentially a single piece of furniture sitting in an empty room. The rest of the development around it is still years away. The total cost of Madrid Nuevo Norte is estimated at around 15 billion euros, making it the largest urban development project currently underway in Europe. The financing model is unusual. Rather than the government footing the entire bill, the project is structured so that the developer, a joint venture involving Spanish infrastructure giant BBVA and the national rail operator ADIF, funds construction partly through the value generated by selling the land and buildings that the development itself creates. In theory, burying the tracks unlocks so much real estate value that the project largely pays for itself over time. Whether that model holds up as construction costs rise across Europe is a question that will take years to answer. Construction on the station expansion and the underground track infrastructure is already underway and is expected to be completed in phases stretching through the early 2000s and 30s. The first new residential neighborhoods are projected to begin opening around 2030, though timelines on a project this size have a tendency to shift. Given that this particular project already accumulated 30 years of delays before breaking ground, a degree of skepticism about deadlines is probably healthy. What isn't debatable is what this project means for the neighborhoods it has ignored for so long. Districts like Vallecas and Hortaleza, long separated from Madrid's more prosperous center by the railway barrier, will gain new connections, new green spaces, and direct access to what will become one of the busiest transport hubs in southern Europe. The project includes over 300,000 square meters of parks and public space, more than 3 times the size of Madrid's famous Retiro Park, designed to stitch together communities that have spent generations on opposite sides of the tracks. Madrid Nuevo Norte is in many ways the story of a city finally dealing with its own unfinished business. It is one of the most consequential things happening in any European city right now. But the last 3 mega projects in this video are .A size at an unprecedented scale, with number 3 requiring a global effort to make it possible. In the south of France, scientists are building a machine designed to recreate the power source of the sun. If it works, it could solve humanity's energy problems forever. If it doesn't, it will be the most expensive scientific failure in history. Nuclear fusion has been the energy dream for over 70 years. Unlike nuclear fission, which splits atoms apart and creates radioactive waste, fusion smashes atoms together the way stars do, producing massive energy with minimal waste. The fuel is abundant and cheap, with a harmless byproduct in helium. With no meltdowns, no radioactive waste lasting thousands of years, it has been called the holy grail of energy production. There's just one problem. Nobody has ever made it work at a scale that produces more energy than it consumes. Every fusion reactor ever built has been a net energy loss. You pump in enormous amounts of power to make the reaction happen, and you get less power out. Fusion has been 30 years away since the 1950s, a running joke in the scientific community. But a massive international consortium decided to bet $25 billion that this time would be different. ITER, the International Thermonuclear Experimental Reactor, grew out of discussions in the 1980s when the Soviet Union, United States, Europe, and Japan agreed that fusion research was too expensive for any single country. They'd build a reactor together, sharing costs and knowledge. After the Cold War ended, the project expanded to include China, South Korea, and India. 7 partners representing half the world's population committed to building the world's largest fusion reactor in southern France. The site at Cadarache was selected in 2005 after intense lobbying from France and years of political negotiations. Construction was supposed to begin in 2008 with completion by 2016. The budget was estimated at $6 billion. Those numbers now look almost comically optimistic. ITER will use a tokamak design, a massive donut-shaped chamber where hydrogen isotopes get heated to 150 million degrees Celsius, 10 times hotter than the sun's core. At these temperatures, the hydrogen becomes plasma, and the atoms fuse together, releasing enormous energy. Powerful magnets contain the plasma, keeping it from touching the reactor walls, which would instantly vaporize. The whole machine weighs 23,000 tons, 3 times the weight of the Eiffel Tower, and requires components manufactured to tolerances measured in millimeters, despite the extreme temperatures and magnetic forces involved. Construction began in 2010, 2 years late. Almost immediately, problems emerged. The tokamak's design was so complex that manufacturing the components pushed engineering to its limits. The main vacuum vessel, the heart of the reactor, requires welding techniques that had never been attempted at this scale. Each segment weighs hundreds of tons and must fit together with near-perfect precision. Early manufacturing attempts failed quality tests and had to be scrapped. The magnets proved even more challenging. ITER uses superconducting magnets cooled to minus 269 degrees Celsius, just 4 degrees above absolute zero, to generate magnetic fields powerful enough to contain plasma at 150 million degrees. These magnets are the largest ever built, and keeping them cold while they sit meters from something hotter than the sun's core requires insulation systems that barely existed when ITER was designed. Multiple magnet coils failed testing and required complete redesign. Then there were the purely logistical nightmares. Components built in Japan, Korea, China, Russia, Europe, and the United States had to be transported to southern France and assembled like an impossibly complex puzzle. Some pieces were too large for normal roads. Special transport routes had to be built through French villages, with houses temporarily relocated and power lines moved. A single component delivery could take months and cost millions in logistics alone. By 2016, the year ITER was supposed to start operating, construction was only about 50% complete, and the budget had tripled to $18 billion. The partners held crisis meetings to decide whether to continue. Some wanted to cancel the whole project. Fusion was taking too long and costing too much, and maybe the money would be better spent on renewable energy that actually works. But canceling meant writing off over a decade of work and billions already spent. The partners agreed to continue, but imposed stricter management controls and pushed the completion date to 2025. That 2025 date has now slipped to 2035 for first plasma, the moment when ITER will actually attempt fusion reactions. Full operation won't happen until 2039 at the earliest. If everything goes perfectly from here, the budget has climbed past $25 billion and will likely go higher. ITER has become the most expensive scientific experiment ever built, surpassing even the Large Hadron Collider. The delays have real consequences beyond just money. Countries have questioned whether to keep funding a project that seems to never deliver results. China has started building its own fusion reactors independently, no longer willing to wait for international collaboration. Critics argue that ITER's management structure, 7 international partners all needing to approve decisions, makes it impossible to move quickly. Each partner manufactures different components in their home countries, prioritizing domestic jobs over efficiency. The result is a project that costs far more and takes far longer than if a single entity controlled it. However, the Large Hadron Collider faced similar setbacks and is now producing groundbreaking physics. Apollo went over budget and behind schedule, but still reached the moon. ITER may well follow a similar path, opening the door to a new era of clean energy. As of 2025, the tokamak is about 80% assembled. The massive building housing the reactor is complete. Components continue arriving from partner countries and getting installed. The control systems are being tested, barring catastrophic problems. First plasma should happen sometime in the mid-2030s, the moment when hydrogen actually fuses inside the reactor and proves the design works. But even if first plasma succeeds, ITER won't generate electricity. It's an experiment, not a power plant. The goal is to produce more energy from fusion than the reactor consumes. If it achieves that, commercial fusion power plants might follow in the 2050s or 2060s. That construction goals are set far away in the future. However, with clear advantages over renewables, fusion remains attractive Even if it arrives decades late, ITER's legacy won't be clear until the 2030s at the earliest. If the reactor successfully demonstrates sustained fusion reactions, it will vindicate decades of research and $25+ billion in spending. If it fails, the entire fusion power dream might collapse as investors and governments lose patience with a technology that perpetually promises results in just a few more decades. From France's fusion reactor that might work in 10 years, we head to Britain's wind farms that are already generating power today. The North Sea has been making Britain rich for 50 years by pumping oil and gas from beneath the seabed. Now those reserves are running dry, production is declining, and Britain needs to figure out what comes next. The answer turned out to be covering a massive chunk of that same North Sea with wind turbines. So many turbines that the project will produce more electricity than any other offshore wind farm on Earth. Dogger Bank sits 130 kilometers off England's northeast coast in relatively shallow water that's been a fishing ground for centuries. The sandbank beneath the waves was dry land 10,000 years ago, before sea levels rose after the last ice age. Fishermen have worked these waters for generations because fish congregate there in huge numbers. Now, energy companies see something more valuable: strong, consistent winds and shallow enough water to make building massive offshore wind farms economically viable. Britain started pushing offshore wind in the 2000s as North Sea oil declined and climate commitments required cutting carbon emissions. The government offered subsidies and guaranteed power prices to encourage development, and companies started building wind farms in shallow waters close to shore. Those early projects were small by today's standards, a few dozen turbines producing maybe 100 megawatts. They proved the concept worked, but didn't move the needle on Britain's overall energy supply. Dogger Bank is different. When complete, it will have 3.6 gigawatts of capacity, enough to power 6 million British homes, roughly 5% of the entire country's electricity demand. The project is being built in 3 phases called A, B, and C, each with 1.2 gigawatts. The turbines are genuinely massive. Each one stands 260 meters tall from sea level to blade tip, taller than London's Shard. The blades are 107 meters long, meaning the rotor sweeps an area larger than 3 football pitches as it spins. Each turbine produces 13 megawatts, among the most powerful offshore turbines ever deployed. When all 277 turbines are operating, Dogger Bank will generate enough electricity every day to power major British cities. But building it has been harder than anyone expected. Construction started in 2020, and almost immediately, the project hit problems. Getting equipment and workers offshore during a pandemic proved nearly impossible. Supply chains for massive turbine components collapsed as manufacturers in Europe and Asia shut down. Specialized installation vessels, the jackup ships needed to install turbines 130 kilometers offshore, were in short supply because multiple wind farms were competing for the same equipment. The cables alone turned into a nightmare. Undersea cables must carry electricity 130 kilometers from turbines back to shore, then connect to Britain's national grid at 2 onshore substations in Yorkshire. Each cable costs over $100 million and requires specialized cable-laying ships that book up years in advance. The cables must be armored against damage from ship anchors and fishing nets, buried in the seabed where possible, and tested extensively before going live. Installing all the cabling for 3 phases has taken years longer than originally scheduled. Environmental groups fought the project over impacts on marine life. The monopile foundations, massive steel cylinders hammered into the seabed, create noise that can harm porpoises, seals, and fish. Pile driving sounds carry for kilometers underwater, and marine mammals depend on sound for communication and navigation. The developers were forced to use bubble curtains and schedule pile driving to avoid migration periods, adding time and cost to every installation. Then came the supply chain crisis that hit Britain particularly hard after Brexit. Components manufactured in Europe suddenly faced customs delays and regulatory issues that didn't exist before. Wind turbine nacelles, the housing containing the generator, got stuck at ports waiting for paperwork. Specialized ships needed permits to operate in British waters that took months to process. Brexit didn't kill the project, but it added countless delays that pushed timelines back repeatedly. Dogger Bank A, the first phase, finally began generating power in late 2023 after delays pushed completion back from the original 2022 target. Turbines started spinning and feeding electricity into the grid, validating that the whole system could actually work. But getting the remaining phases operational has been slow. As of early 2025, Dogger Bank B is still under construction, with turbines being installed throughout the year. Dogger Bank C hasn't started turbine installation yet and won't be complete until 2026 at the earliest. Once complete, maintenance will be the long-term challenge that makes or breaks Dogger Bank financially. Offshore turbines face brutal conditions, and getting repair crews to turbines 130 kilometers offshore is expensive and weather-dependent. Dogger Bank will hold the title of world's largest offshore wind farm for a few years until other projects under construction in Asia and Europe overtake it. But for now, it represents the peak of offshore wind ambition. The largest turbines, the deepest water, the farthest from shore, generating more power than any comparable project. Whether it becomes a template for future wind farms or a cautionary tale about pushing technology too far too fast won't be clear until it operates for years and the maintenance costs become real. From Britain's massive wind farm finally taking shape, we head north to Denmark, where an even more audacious offshore energy project is being planned. Denmark generates over half its electricity from wind power, the highest percentage of any country on Earth. The country has committed to ending fossil fuel use entirely by 2050, and to make that happen, the government announced something in 2020, building artificial islands in the North Sea that exist purely to collect wind power and distribute it across Europe. The concept seems absurd at first. Construct islands 80 kilometers offshore in some of the world's harshest waters. Surround them with hundreds of massive wind turbines. Use the islands to house equipment that converts and transmits the electricity, then send that power to Denmark and neighboring countries through undersea cables. Denmark's government presented the energy islands as the solution to multiple problems at once. Offshore wind farms keep getting built farther from shore, where winds are stronger and more consistent. But running cables from each wind farm back to land is expensive and inefficient. The islands would act as collection hubs. Multiple wind farms connect to the island, and a single high-capacity cable runs from the island to shore. It's more efficient and allows Denmark to build wind farms in deeper water farther offshore than is currently practical. The plan calls for 2 islands. The North Sea island will be completely artificial, built from scratch 80 kilometers off Denmark's west coast in water about 30 meters deep. It will cover at least 120,000 square meters, roughly the size of 18 football pitches, and host equipment to handle 10 gigawatts of wind power when fully developed, equivalent to Denmark's entire current electricity consumption. The Baltic Sea island will use the existing island of Bornholm as its base, adding facilities to handle 3 gigawatts from surrounding offshore wind farms. Building artificial islands isn't new. Dubai built several, and Hong Kong's airport sits on reclaimed land. But building an island 80 kilometers offshore specifically to harvest wind power had never been attempted. The engineering challenges are enormous, the costs staggering, and the timeline extends decades into the future. Energy experts questioned whether Denmark was being visionary or delusional. The $34 billion price tag immediately became controversial. Denmark is a small country of 6 million people, and $34 billion represents a significant chunk of national wealth. The government insisted that private companies would fund most of the construction through public-private partnerships, with pension funds and international investors putting up capital in exchange for long-term electricity revenue. But getting private companies to commit billions to a project that won't generate returns for decades proved harder than expected. The North Sea island presents engineering challenges that don't have obvious solutions. Workers will need to dredge millions of cubic meters of sand from the seabed and build it up into a stable island capable of withstanding North Sea storms that regularly generate waves over 15 meters high. The island must support heavy equipment, high-voltage substations, power conversion systems, control buildings that can't be flooded or damaged by storm surges. Everything must be designed for an environment where humans can't permanently reside because conditions are too harsh. Construction methods are still being debated because nobody has done anything like this before. The current plan involves caissons, massive concrete boxes that get floated to the site, filled with sand, and sunk to form the island's foundation. On top of that, workers would build the actual island surface and install all the electrical equipment. The whole process will take years and require calm weather windows that are rare in the North Sea. One bad storm during construction could undo months of work. Denmark's parliament approved the Energy Island legislation in 2021, and detailed planning began immediately with great enthusiasm. But by 2023, problems were emerging. The initial timeline called for starting construction on the Baltic island by 2024 and the North Sea island by 2026, with both operational by 2030. Those dates have already slipped as the technical realities became clearer. Current estimates suggest the Baltic island might see first power by 2030, while the North Sea artificial island won't be operational until the mid-2030s at the earliest. When the islands were announced, Denmark highlighted plans to use excess wind power to produce green hydrogen through electrolysis. The hydrogen could be stored, used for power generation when wind is calm, or exported to industries that need it. This sounded great in theory, but green hydrogen production at scale has proven far more difficult and expensive than expected. By 2024, most energy analysts were skeptical that hydrogen would be economically viable anytime soon, casting doubt on a key part of the island's business case. As of 2026, no construction has started on either island. What exists are detailed plans, feasibility studies, environmental assessments, and political commitments. The engineering firms, turbine manufacturers, and construction companies that would actually build the islands are still working through technical challenges. The offshore wind farms that will surround the islands haven't been approved or built. The undersea cables that will transmit power to shore and to neighboring countries haven't been laid. Denmark keeps insisting the project will proceed, but the timeline keeps stretching and the cost estimates keep rising. Some politicians have started quietly suggesting that maybe the artificial North Sea island is too ambitious and Denmark should focus on the simpler Bornholm project in the Baltic. Others argue that abandoning the plan would be an embarrassing admission of failure and would damage Denmark's reputation as a climate leader. The Energy Islands is an audacious vision that could either establish Denmark as Europe's renewable energy hub or become an expensive lesson in the limits of what's actually buildable in the harsh North Sea. But what do you make of Denmark's vision? Will any of these insane construction dreams turn into reality? Comment your thoughts below. From Europe, you can take a journey to United States of America by checking out America's biggest megaprojects under construction in 2026. Keep following SIGNUM for more mega builds from around the world.